Right. So last class we have started our discussions on graph theory, particularly the network models, and as I have said in the previous class already, that in this particular discussion on networks we are basically discussing the graph theoretical concepts specifically for the network flow problems and the shortest path problems, right. Basically the kind of problems that would be really required to solve these kind of network related problems only. And graph theory is a vast subject, and this particular theory is also used for a lot of other applications, specifically the computer science related applications. So, if you take a very quick recap, what I said on the previous day, that a graph is a set of edges and vertices, and there are certain things about a graph that the vertices, two vertices are adjacent if there is an edge between them, and these edge is incident on those particular vertices, and number of edges incident on a particular vertex is called the degree of that particular vertex. So, some of these concepts we have discussed in our previous class. Let us continue from there. So, today we shall see certain kind of concepts. The first one is a work. Now, what is an work? And work is a finite alternate sequence of vertices and edges beginning and ending in vertices, with each edge incident on vertices following and preceding it. Now, I do not know what you really understood from this particular definition, but let us really try to see what it is by looking at a particular graph. So, suppose we have a particular graph like this. Let us take a very simple graph. So, suppose we have a graph like this. Right. So, suppose this is V1, this is V2, this is V3, this is V4. There are 4 vertices, and let us say there are 5 edges. Right. So, a very simple graph with 4 vertices and 5 edges. So, work will be, let us say we start with V1, then it should be an alternate sequence of vertices and edges starting from vertices. So, we started at V1, then let us say we take E1, we go like this. So, we can take another pen. So, from V1 we go to V2, right. So, that is the first leg, right. Then after that we might come to another vertex V3, then we may go to another vertex V4. So, V2 to E4 to V3 to E5 to V4, right. Now, you may question that if from V4 can we go to V1? Answer is no, we cannot go. Why? Because there is no edge available between V4 and V1. Alright. So, from V4 suppose we again come back to V2. So, V4 E3 to V2, and then we may take that path once again. So, we take that path one more time, second time, just look, we have gone second time. So, V2 to E4 to V3. So, this is an work. So, what is an work? Work is an sequence of vertices and edges starting from vertices such that each edge considered is incident on the vertex, right, and while doing so we can repeat both vertices and edges, right. So, that is the concept. So, it is a most general, but then again there are two kinds of work. There is open work and closed work. So, the kind of work that we have taken just now, is it open work or closed work? See, if the starting vertex and the ending vertex is the same, then it is a closed work. So, a simple thing we say that an open work we call it an UV work with U not equal to V, right, and a closed work is an UV work where U is equal to V. So, that is the difference between the open and the closed work. So, same thing you just now understand this, that open work in this particular graph V1, E2, V2, E3, then V3, then E5, V4, then E4, V2, and then again E3, V3. Is it all right? So, closed work starting at V2 and ending at V2. So, V2, E3, V3, E5, V4, E4, V2, E3, V3, and then E3 again E3, V2. So, starting at V2 ending at V2, right. So, this is called an work. Now, the next term what is important in this context is called a trail. So, what is the difference between a work and a trail? The trail is also an work, but all trails are not works. What is the difference? That here no edges can be repeated, right, edges cannot be repeated, but vertices can be repeated. Is it all right? So, in this case let us look at some trails. So, trail, one trail could be that V1, E2, V3, E4, V2, right. So, V1, E2, V3, E4, V2, that is the trail, right. Supposing if we have V1, E2, V3, right, V1, E2, V3, then E4, V2, E3, and then continue V4, E5, V3. So, you see here the V3 is repeated, right, the same we have gone like this, we have gone like this, and we have finally ended here. So, this one is a trail definitely because no edge is repeated, but it is not a what is known as a closed trail, is a open trail. What happens in a closed trail? In a closed trail we have a particular if you look at a closed trail, just look at a closed trail, the closed trail would be V1, E1, V2, E4, then V3, then E2 and V1. So, this is a closed trail, right, this is a closed trail, right. So, that is what, that no edges should be repeated. Now, after that let us look at the next one, that is called a path. A path is basically is a trail with no vertex repeated, right. So, we have the work where vertices and edges both are repeated, a trail where edges are not repeated, but vertices can be repeated, and finally, the path where neither vertices nor edges can be repeated, right. So, here in this diagram, so look at this, that V1, E2, V2, E2, V2, E3, V3, E5, V4 is a path, right, and closed path is called a circuit. So, what is a closed path? So, V1, E2, V2, E3, V3, E1, V1. So, in this case, see what is happening, the beginning and ending vertices are same, right, beginning and ending vertices same, but no other vertices can be repeated. So, some question may be raised that how come it is a path, because this beginning vertex is repeated, but we call it a circuit. So, that is a closed path. So, more about the circuits and other things later, and let us now continue and see a particular problem that we are calling the Konigsberg bridge problem. So, you see this is a very interesting problem. The problem, as you can see, let us draw this, the Konigsberg bridge problem. In this case, supposing there are two land masses in a river, right. So, this is the river, and in this river there are two land masses, and there are two more land masses on the both sides of the river. So, we have got therefore 4 land masses. What are these? This one is L1, let us say this is L2, this is L3, and this is L4. Now, these 4 land masses are connected by 7 bridges. So, what are those 7 bridges? This is one bridge, this is another bridge, this is another bridge, this is another bridge, this is the 5th one, 6th one, and 7th one. Alright. So, these are the 7 bridges. Let us name those bridges. There is a B1, this is B2, this is B3, B4, B5, B6 and B7. So, there are 7 bridges, they are available in this particular river, and connecting the 4 land masses. So, what is to be done? What we have to do is start from any of the land masses. Let us say L1, start at L1. What you have to do? Cover all the bridges exactly once, right. Cover all the bridges exactly once and come back to the same bridge, right. Cover all the bridges exactly once and come back to the same bridge. So, you see, supposing we start from this particular bridge, come to L3, again come to L1. Now, you can come to a landmass more than once, right, but the bridges should be covered exactly once. Question is it possible or not possible, right? That is the question. What is the first task to do is, can we convert this to a network problem? So, that could be our first task. Let us convert this to a network problem. So, which one should be node and which one should be our vertices, right, or node or vertices, and which one should be arcs or edges. So, quick thinking, if you do, you will find these land masses will be like node or vertices, and the bridges are like edges, right. So, this is understood. Once this is understood, then we can convert this to a network. So, let us take the 4 land masses L1, L2, L3 and L4. So, these are the 4 land masses. Now, L1 and L3 connected by 2 bridges. So, look, it is like a parallel edge. Similarly, 2 bridges here, single bridge here and a single bridge here. So, you see, these are the 7 bridges. So, B1, B2, B3, B4, B5, B6, B7. So, this is the graph theoretic representation of the same problem. The question is that starting from a particular landmass, can we move through all the bridges exactly once and come to the same landmass? Let us give an alternate problem to the same thing. Suppose I have a room. And this room has got 4 doors. These are the 4 doors, right. So, call it D1, D2, D3 and D4. These are the 4 doors. Now, question is that say this is room 1 and this outside is part of a bigger room, call it R2, right. So, it is like is a big room, within that this small room is there and this room has got 4 doors. Now, start at R1, go through all the doors exactly once and come back to R1. So, this is the problem, that can we start at room 1, go through all the doors exactly once and come back to R1. Is it practically possible, right? So, in graph theoretic language, how it looking like? So, what should be the graph for this particular problem, right? So, again look here, how many vertices? There are 2 vertices, R1 and R2. So, we can put R1 here and R2 here. And how many doors? There are 4 doors. So, you can connect those 4 doors in this manner, right. So, D1, D2, D3 and D4. Now, tell me, is it possible or not possible? See, very interesting and very easy also. All you have to do, use any of the door from R1, go to R2. Take another door, come back to R1. Take another door, go to R2. Take another door, come back to R1. So, it is a very simple problem and the solution is easily available, that yes, the answer is yes, it is possible. Why? Because you see, from R1 have one door and to go out and another door to come back. Similarly, D3 and D4. So, essentially what it boils down to, that as long as you have those doors in pairs or you have edges in pairs, you can find a solution to such problems, right. Now, let us see that whether it is leading to some theory. So, there are 4 land masses, 7 bridges that we know, and how to cross all the bridges exactly once, starting from any of the 4 land masses and coming back to the same land mass. So, answer of this question we shall see later, but let us look at some concept. That is called a concept of Euler graph. The idea of Euler graph is that in Euler graphs, it is possible to traverse all the edges exactly once, starting from any of the vertices and coming back to the same vertex, right. So, can you now, just now we have gone through the concept of walk, trail and path. So, what does it mean in that language? You see, walk is a concept where it is a set of vertices and edges, where vertices and edges both can be repeated. Trail is a concept where vertices can be repeated, but edges cannot be repeated. And path is a concept where neither vertex nor the edges can be repeated. Is it all right? So, therefore, an Euler graph is really matching with which concept? Here the vertex can be repeated, but edges cannot be repeated, right. Additionally, we are telling you have to go through all the edges. So, it is like a concept of the a closed trail, right. So, the essential idea of an Euler graph, find a closed trail. Euler graph is a concept, a graph that contains a closed trail that covers all the edges, right. So, if you can find a closed trail that covers all the edges, then we can call that is an Euler graph. So, in this particular graph, look at we start with A, go to B, go to G, then go to A, and then go to D, and then go to E, then F, then G, then E once again, and come back to A, right. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, right. So, it is an Euler graph because we have a closed trail, and this is sometimes called an Euler circuit or an Euler line or an Euler trail, right. This crosses every edge exactly once without repeating and ends at the initial vertex, right. So, this Euler trail, in the Euler graph all the vertices are of even degree. That is very interesting. Why even degree? Think of that door problem once again. If you have to come back to the same room, you must have one door for going out, another door for coming back, is it not? So, that means door should be in pairs. So, in this case, if you go out from A from one edge, you must have another edge to come back. If you have come back to A, but still two more edges are remaining. So, again you have to go out in one and come back in another. Same thing should hold for all the vertices, or in simple words, all the vertices should be of even degree, is it not? That is the requirement of an Euler graph, that all the vertices should be of even degree, right. So, that is what we find here, that it must be a closed trail, all the edges should be exactly once. A type of problem that is called the Chinese postman problem, where the basic idea is to find out an Euler trail. So, what is the Chinese postman problem? Look at this graph. Supposing these are the road network in a particular locality. Now, in this locality, on each of the road there are lots and lots of houses, each of the road. So, assume there are 9 roads and each road has got lots of houses. The postman is currently at point A. What the postman would like to do? The postman would like to deliver letters and packages to all the houses. But since the postman has to deliver letters to all the houses, it is therefore good for the postman that what the postman would like is to travel the minimum. Assume the postman is going from A to B and again comes back to A. Then what happened? Road 2 is not covered. So, again the postman then has to go through perhaps 1 and then cover road 2 and then maybe take some path and come back. So, that way the postman may have travelled 3 times, first go and come back and again take 1 and go to road 2. So, this way the total travel of the postman is rather high. So, if an Euler trail is available, then the Chinese postman would be able to really deliver all his or her letters to all the houses by covering the minimum distance. So, there must be lot of equivalent problem which are akin to this problem. In all these problem, essential idea is, can we find an Euler trail? Now, while discussing Euler trail, a closely related problem is what is known as finding an Hamiltonian circuit. The Hamiltonian circuit is, it covers every vertex exactly once and while beginning and ending at the same vertex. So, what is the difference? The difference is, earlier we are covering all the edges, now we have to cover all the vertices exactly once. So, maybe you can go from A to B, then C, then D, then E, and then come back to A, right. So, assume these are all the possible path sequences. So, A, B, C, D, E is a Hamiltonian circuit. Now, are there more circuits? In fact, you may find there are hundreds of such circuits, right, that you can also take AC, BE, DA. What is very interesting to note that all these Hamiltonian circuits, they are not of the same length, right, because you see, if you go from A to B, look in that second path, that A, C, A, there is one path that goes through A, B, C, D, E. So, A to B is included. In the second path, when you take A, E, B, D, C, A or A, C, B, E, C, D, A, B path is not there, another set of 5 paths are there. So, what is the difference? The difference is that all these path lengths will not be same. Is it all right? So, the Hamiltonian circuits that we shall have, they all will have different kind of, if there are weights, suppose if it is a road network and there are distances. So, distance is like a weight. So, all these distances when you add together, you may find that total distance is different in different paths. So, natural question that comes is that which path should one consider in order to travel the minimum. Such a problem is called a travelling salesman problem, right. So, essentially the solution is nothing but a Hamiltonian circuit. The idea is the salesman has to go from one city to all the cities exactly once. What should be the path the salesman should follow so as to travel the minimum, right. A related concept could be, the quickly let me show, then we will come back here, is called an arbitrarily traceable Euler graph. So, this is also an Euler graph. The only difference is that at every vertex you reach, you have the choice to choose any of the paths that you like, right. So, here if you come here, then suppose at this point, if you decide to go back this way, then you do not cover all these things. So, is it arbitrarily traceable? So, these are interesting questions. Here suppose you go from A, B, G and then you decide to take another path, right. So, it may be that a particular graph has an Euler graph, like here see every degree is even. So, there is an Euler path, but question is that sorry, not Euler path, the Euler trail, but in this case is there an is it arbitrarily traceable, right. Arbitrarily traceable, suppose here you decide to go back, again you come back, but you do not cover this. So, it is not. So, same thing here also. So, if you can do that, such a graph is called an Euler graph, right. So, before I end, let us try to see what should be the solution to the Konigsberg bridge problem. So, this is the problem and this is the graphical representation. Look at the degrees. What is the degree at A? It is 1, 2, 3, 4, 5. What is at D? 3. At B 3 and C also 3. So, since the degrees are not even, right, will there be an Euler graph? Answer is no. This graph is not an Euler graph and there is no Euler trail. Since no Euler trail is there, this solution is not possible. So, all right. So, we discussed some of the very important graph theoretic concepts today and I stop here. We will continue our discussions, but now this time we will see some operations on graph and then the most important concepts of tree and spanning tree. Thank you very much.